Welcome to the introduction to manufacturing. Today we'll be covering polymers, which is the third topic out of three that we have covered so far. So what are polymers? A polymer is a compound consisting of long chain molecules. Each molecule is made up of repeating units connected together. You can have a lot of them, thousands, even millions of them in a single polymer molecule. And so if you look at the word polymer, that is derived from the Greek word poly, which means many. And then the word meros, which reduces to mer, it means part. So if I look at those two words together, most polymers are based on carbon and are therefore considered organic chemicals. So what are the types of polymers that exist? Polymers can be separated into plastics and rubbers, and as engineering materials, it is appropriate to divide them into three categories: thermoplastic polymers, thermosetting polymers, and elastomers. And number one and two are considered plastics, and three are considered rubbers. So if I look at thermoplastic polymers, which we also call thermoplastics in short, solid materials at room temperature but are viscous when heated to temperatures of only a few thousand degrees or a few hundred degrees even. So these materials are room temperature but can become viscous when heated. These characteristics allows them to easily be shaped into products that are used here today. You can see some of them on the top on the left. They can be subjected to heating and cooling cycles repeatedly, but you will not get a significant degradation from them. It's also symbolized as TP, thermoplastics. You may see that out there. And examples of thermoplastics include polyethylene, polyvinyl chloride, PVC, polypropylene, PP, polystyrene, PS, and then nylon. So you've seen products made of these materials. Thermosetting polymers, which are thermosets, they cannot tolerate repeated heating cycles as thermoplastics can. So once you have a thermoset and you try to heat it up, it will be very difficult to bring it back to the original state. When initially heated, thermosets will soften and flow for molding, and at elevated temperatures also produce a chemical reaction that allows them to harden the material into infusible solid. And the issue there is that if you reheat thermosets, the thermosets will degrade and char, but it will not soften back to the original state. So these are symbolized as TS. Examples of thermosetting polymers include phenolics, epoxies, and certain polyesters. Now let's look at the third group of polymers, elastomers, rubbers. Polymers that exhibit extreme elastic extensibility. And this occurs when you subjected them to relatively low mechanical stress. Rubber bands is one example, or a little duck toy. Some elastomers can be stretched by a factor of 10 and yet completely recover to the original shape. Although their properties are quite different from thermosets, they share similar molecular structure that is different from many thermoplastics. Examples of that include natural rubber, synthetic rubbers, and so forth. So thermoplastics are commercially the most important of the three types, although all three are used in aerospace and mechanical application. About 70% of the tonnage of all synthetic polymers are produced. Thermosets and elastomers share the remaining 30% about evenly, and on a volumetric basis, the current annual usage of polymers exceed that of metals because they're cheaper, they're easy to manufacture using these materials, and the reason polymers are important is because plastics can be molded into very complex shapes, usually with no further processing. And it's very compatible with net shape processing, very little waste. On a volumetric basis, polymers are more cost competitive metals. They generally require less energy to produce than metals, and certain plastics are translucent or transparent, which is really competitive for glass and some other applications. So what are the general properties of polymers? Low density relative to metals and ceramics, a good strength to weight ratio for certain polymers, high corrosion resistance. You're going to have very little corrosion issues with these materials, low electrical and thermal conductivity. So very nice. Limitation of polymers, however, they're low strength, so you can't use them everywhere. Low modulus of elasticity. Surface temperatures are really limited to a few hundred degrees. Viscoelastic properties can be very nice, but can be a limitation for load-bearing applications. Some polymers also have additional degradation mechanisms like for the space environments, when they're subjected to sunlight or radiation, they can degrade as well. Now, polymers embedded with fibers, like carbon fibers, and that makes composites there, they can provide significant benefit there in that application. The synthesis of polymers is as follows. Nearly all polymers in engineering are synthetic today. They're typically made by chemical processing, and they're synthesized by joining many small molecules together into very large molecules. We call them macromolecules. And they possess a chain-like structure, which allows them to behave the way they behave. The small units, we call them monomers, and are generally simple unsaturated organic molecules, such as ethylene. And here you have two molecules of carbon and four of hydrogen. You can see here that repeating these produces a polymer. So the degree of polymerization, since molecules in a given batch of polymerized material vary in length, here N for the batch is an average. So it's a statistical distribution tends to be normal. The mean value of N here is called the degree of polymerization, or dP for the batch. dP affects the properties of the polymer. Higher dP increases the mechanical strength, but then it has the negative effect where it can increase the viscosity in the fluid state, which makes processing a lot more difficult. So if I look at the molecular weight of a polymer is the sum of the molecular weights of the mirrors in the molecule. MW is what we call molecular weight. MW is N times the molecular weight of each repeating unit. And since N varies for different molecular batches, the molecular weight must be interpreted as an average. So if I look at the typical values, for polyethylene, you're looking at 10,000. For polyvinyl chloride, which is PVC, 1,500, nylon 120, and polycarbonate 200. But when I look at the molecular weight, you're looking at 300,000, 100,000, 15,000, and 40,000 respectively for these polymers. And here it's a composition, but N is the thing varying. So if you look at the polymer molecular structure, in A, you can see a linear structure, which is chain-like structure. They're characteristic of thermoplastic polymers. Branch structures, which are chain-like but with side branches, also found in thermoplastic polymers. And then cross-linked structures, which are loosely cross-linked characteristics of elastomers. And then here at the bottom, you have tightly cross-linked, which is characteristics of thermosets. And the loose behavior of the cross-linking allows the characteristics you see of elastomers. So what are mechanical properties of thermoplastics? They have low modulus of elasticity, orders of magnitude lower than metals and ceramics, low tensile strength. The tensile strength can be as low as 10% of the metal, much lower hardness than metals or ceramics, and significant amount of elongation capability. Tremendous range of values, 1% to up to 500% for polystyrene or more. Sorry, 1% for polystyrene to 500% or more for polypropylene. When you look at physical properties of thermosets, these tend to be more rigid, and the modulus of elasticity is 2 or 3 times greater than thermoplastics. With thermosets, you get more brittle behavior, virtually no ductility. That speaks a lot to the cross-linking process we talked about, less soluble in common solvents than thermoplastics, capable of higher surface temperatures than thermoplastics, cannot be melted. Instead, they can degrade or burn. The cross-linking in these thermosets have three categories. You have temperature activated systems, catalyst activated systems, and mixing activated systems. Curing in these cases is accomplished at the fabrication plants that allow making the parts rather than the chemical plants that supply the starting materials to the fabricator. So what about thermosets versus thermoplastics? Polymers. Thermosets, plastics are not widely used as thermoplastics. We've talked about that. And one reason is the added processing costs and complications involved in the curing process. Composites is, may have heard of composite materials where you take an epoxy and you have carbon fibers. That's a thermoset that requires a curing process in an autoclave. The larger market share of thermosets is phenolic resins with 6% of the total plastic markets. And then compare that to polyethylene, which is only 35% market share. So thermoset products, you may have silicone countertops, plywood adhesives, paints, molded parts, printer circuit boards, and what I just said, fiber reinforced composites. When I look at elastomers, these are polymers capable of large elastic deformation when subjected to relatively low stresses. Some can extend up to 500% or more and still come back to the original shape, which is quite amazing. Two categories: natural rubber, derived straight from biological plants; synthetic rubbers, which are produced by polymerization processes similar to those used for thermoplastics and thermosetting polymers. So if I look at natural rubber first, natural rubber consists primarily of polyisoprene, which has a high molecular weight polymer of isoprene of C5H8. It is derived from latex and is a milky substance produced by various plants, most important of which is a rubber tree that grows in tropical climates. Latex is a water emulsion of polyisoprene, about one third of the weight by weight, plus various other ingredients. Rubber is extracted from latex by various methods that remove the water. And then we have another process called vulcanization, which is curing to cross-link most elastomers. So this is the vulcanization process, which is a term for curing in the context of natural rubber and certain synthetic rubbers. Typical cross-linking in rubber is 1 to 10 links per 100 carbon atoms in the linear polymeric chain, depending on the degree of stiffness desired. Natural rubber is used quite a bit. The largest single market for natural rubber is automotive tires. You can see them. Other products include show tools, bushing seals, and many shock absorbing components. In tires, carbon black is a very important additive because it reinforces the rubber, first of all, but it serves to increase the tensile strength, which is important to resist the tear and abrasion that these materials will be subject to. Other additives that you may see out there is clay, kaolin, silica, talc, and calcium carbonate, as well as chemicals that accelerate and promote vulcanization. Now, synthetic rubbers is also very important, and the development of synthetic rubber is motivated that by the world wars, and also natural rubber was very difficult to obtain. Today, tonnage then of synthetic rubber is a lot more, 3 times more than natural rubber. The most important synthetic rubber is styrene butadiene rubber, or a polymer of butadiene, so C4H6, and styrene, which is CaH8. As with many most polymers, the main raw material for synthetic rubbers is petroleum. So, what is a guide to the processing of polymers in general? Polymers are nearly always shaped in a heated, highly plastic state. Common operations are extrusion, and molding of thermosets is more complicated because of the cross-linking process. So we talked about thermosets, very difficult to cross-link, but it is possible. And thermoplastics are easier to mold, and greater variety of molding operations are available. And then finally, rubber processing has a longer history than plastics, and rubber industries are traditionally separated from plastic industry, even though processing is similar. With that said, I want to thank you for listening to this lecture, and I hope you learned that polymers are a very effective material to be used in a wide variety of manufacturing operations, particularly molding, due to their cross-linking that allows them to be molded with very near net shape processes with very little waste. Very widely used in aerospace, mechanical, and industrial industries. Thank you for your attention. Have a great day.